All right, hello everyone. Thank you for attending the final day of the NESS MTV Summer School. Sorry. Today we'll be having Professor Alan Selinger giving a talk over the chemistry and physics of plastic scintillators. Professor Selinger is a professor conducts research at the Colorado School of Mines in both the design, synthesis, and characterization of novel materials for solar cells and radiation detection, as well as a few other applications. Before we start, I'd like to make a few bookkeeping announcements. For one, keep we will not be using the raise hand feature during this lecture, and all your questions will be just put into the Q&A section of the webinar, which will be addressed at the final 15 minutes of the presentation. And with that, Professor Selinger, you are free to start.
Okay, thank you for the introduction and welcome everybody from all over the world to this presentation on the chemistry and physics of plastic scintillators. So as Ethan mentioned, I am a chemistry professor. I do research mainly in organics and polymer synthesis, and we've been working on plastic scintillators for about 12 or 13 years. And so the image on the screen is of some 3D printing that we've done on making plastic scintillators, but I won't be talking about that today. And on the left is uh, a trace of a PSD, a pulse shape discrimination plot of one of our recent organic glass scintillators that shows the separation of neutrons and gamma lobes that hopefully I will be able to get to today. So just to let you know, many of you may not know where Colorado School of Mines is. So here's a map of the United States, and we are located here close to the Denver area. And if we zoom in a bit closer, you can see here is Denver, and here is the Colorado School of Mines. And all of this is the Rocky Mountains. So we are as far west as you can go to the Rocky Mountains. And just a little bit of information, the Colorado School of Mines is primarily a science and engineering university. So all students are basically either engineering or in science. It's a fairly a tough school to get into. Is generally over 12,000 applications for about 1,400 spots. It's one of the top engineering schools in the United States, and recently we have hit this R1 status. That means that we consistently have over $100 million in external research funding. I work primarily in the chemistry department. Our PhD degree is in applied chemistry. Our faculty is about 40% female. Our undergrads are 65% female. And we have about $10 million of external funding in our department. The other thing about our university is that we are pretty high up. So we are about 1700 meters in elevation, and we have mountains very close by that are over 14,000 feet. So it's a nice place to go skiing and to hike in the mountains. And here is just another view showing the Rocky Mountains just west of where we're located. And so to get to these locations is less than an hour driving. Some views of our campus. So this is the center of our campus. This is a hike that I take sometimes before I lecture, so very close to our building. Here is Alpine Glacier that's close to our department. And this is in August, so we can leave our department. It's about 30 to 35 Celsius. And when we get up here, it's much cooler and we can have snowball fights in August. And this is my drive to work. So very nice place. So hopefully you can come and visit sometimes. Okay, so plastic organic scintillators for radiation detection. So here's just kind of a definition of what a plastic scintillator is. Basically materials that emit light when exposed to ionizing radiation, such as alpha particles, beta particles, or gamma rays. They're primarily composed of an organic polymer that have some fluorescent dopants inside. And so I'll discuss a bit how these work next. So first of all, the primary application for these plastic scintillators are in portal monitors. And so this is a picture of a shipping yard, for example, where every single container that arrives to that shipping yard ends up on a truck, and that truck ends up leaving. Before leaving, it has to go through a series of detectors, one of which is a plastic scintillator. And that plastic scintillator could be in one of these yellow towers. And it is basically screening um, for some kind of special nuclear material that somebody is trying to move out of the container. So one of the things is that the the um things that you would be looking for are uranium or plutonium, but of course you could have a container filled with something like kitty litter or granite or bananas, and there's enough accumulation of potassium 40 in a container filled with bananas that could set these off. And so you want to be able to look primarily for special nuclear materials and not have to open every single container that sets these things off. And so that's one of the focus of our project here, is to try to develop plastic scintillators that can screen between neutrons and gammas. So there are detectors that exist. So some are based on helium-3. That's mostly looking for neutrons. Of course, that is a gas, so that's hard to contain, so it's tough to work with. There are single crystals of inorganic materials or of organic materials. These are also very good at both screening for neutrons and gamma. However, making large crystals can be very time consuming and very expensive. And so from an economical standpoint, you can't make these very large. Liquids are also something that's used quite a bit. However, it's a liquid, so it's hard to contain. It also needs to be under non-oxygen conditions because the oxygen will affect its ability to detect. So lastly, there are plastics. And so plastics are cheap, easy to make, but up until recently, they didn't have this ability to to efficiently detect between gammas and neutrons. And so that's kind of where we're working as chemists to try to see if we can make better plastic scintillators. So the way these work is that you have a piece of plastic shown here. There are some source of neutrons or gammas. These come in, and they actually make these scintillators emit light. And so then that light is detected by a photomultiplier tube, and then that data is analyzed by a computer through some kind of data acquisition um, and put into some kind of a graph where you can make some sense out of it. So usually that matrix in commercially available plastic scintillators is a polymer. And so that can be a polystyrene derivative like polyvinyl toluene, of which you have some kind of a fluorescent compound that is added to the matrix in amounts that can be from 1 to 25 weight percent. And then finally, there's a wavelength shifter, and that's basically to funnel all the light out at the emission of this wavelength shifter. And I'll talk about that more in a second. So the radiation comes in. It primarily excites because the polymer matrix is there in a larger amount, it's going to statistically hit the matrix. So that matrix will be excited, and it will transfer its energy to the dopant. The dopant will then emit, and then all of that emission will be absorbed by this wavelength shifter and then re-emitted the wavelength of the wavelength shifter. And so the main reason why we use wavelength shifters is because the photomultiplier tubes are sensitive in the blue light region. And so basically wavelength shifters are only used because the photomultiplier tubes are most sensitive in the area where this would emit. So there's a big push now on getting away from photomultiplier tubes and moving towards, say, silicon photodiodes. And in that case, there would not be any more restrictions on having these scintillators emit blue, because the silicon photodiode can sense many different wavelengths of light. And so then that would be a opening for chemists to be able to um, choose other types of fluorescent dopants that could be used with the newer developments of these detectors. So basically, the main function of the polymer is to absorb and transfer that energy to the primary dopant. It needs to be transparent and needs to be able to solubilize the dopant, and it turns out it needs to have this aromaticity, which means it needs to have these basically these benzene rings that can absorb the incoming radiation and then transfer that energy to the primary dopant. So the primary dopant is basically the active component. It fluoresces depending on the ionizing radiation source. It will generate a different amount of triplet and singlet states, and it needs to be soluble in the polymer upwards of 20 weight percent in order to achieve the pulse shape discrimination that I talked about earlier, and I'll talk about more. It needs to have a spectral overlap with the secondary dopant, which means the emission needs to overlap with the absorption of the wavelength shifter. And it needs to be able to transfer triplets efficiently and have a high photoluminescent quantum efficiency. Lastly, the wavelength shifter needs to be able to absorb the light coming from the primary dopant and then efficiently emit that so that it can be detected by the photomultiplier tube. All right, so how does this work? So when a neutron comes in, it generates some spectrum. A gamma ray comes in, it generates some spectrum. So there is what's called a different amount of prompt and delayed fluorescence depending on that incoming radiation. So as you see, if we just choose an arbitrary cutoff time, you can see that these curves are different, such that the area of the delayed fluorescence is larger than the area of the prompt fluorescence. And so basically, you would get a spectrum that looks like this, where if you did have the ability to discriminate between neutrons and gammas, this would be what your spectrum would look like. You would have a delayed energy fraction of neutrons and a delayed energy fraction of gammas. And so this is how these materials separate neutrons from gammas based on the prompt and delayed amount of light that's coming from these scintillators. And that basically is because of neutrons generating more triplet states. Triplet states then can diffuse and find each other and annihilate and generate what's called a delayed fluorescence. So this difference between the neutron and gamma is what's referred to as the figure of merit. And so the bigger the difference, the better. And so this whole process is called pulse shape discrimination, and then this number is quantified just statistically with this figure of merit. So when we look more carefully at this matrix, you can see that most of it is just a commodity polymer like polystyrene. The next amount is the primary dopant, and then a very tiny fraction is the wavelength shifter, and that 0.1% is enough to completely get all of the energy out at the wavelength of that 0.1% material. So Natalia Zaitseva, who is a really amazing scientist in this area, about 8 or 10 years ago, discovered that if you overdope the dopant into the polystyrene, you can achieve pulse shape discrimination properties. And so here you can see that when you dope this PPO dopant at 25 weight percent, you can get a figure of merit that is about 1.7, and that is very, very good. However, you can see that as a consequence of adding that dopant, the hardness of the material goes down. And so this is one of the main issues of these high fluorescent dopant loading plastic scintillators is that they are just very soft. So um, then they can't be used because if they're put into those big portal monitors, they don't have enough um, mechanical properties to hold their weight and they would deform and the dopants diffuse, and so they just have poor stability. So you can see here scintillators that we've made with high concentrations of dopant over time will eventually, these dopants will crystallize out and you no longer have a transparent material. And so when the ionizing radiation comes in, the light is not able to get out because it's no longer transparent. And so this is one of the big problems, and this is something that we wanted to tackle. But first, I want to let you know how plastic scintillators are made. So this is done by what's called a thermally initiated radical bulk polymerization. So basically we have a vinyl toluene or styrene monomer. So that's before it's polymerized, it's a liquid. And that liquid will dissolve these thermal initiators. They'll dissolve all the dopants. And so you're basically just making a solution of all these components, and then you heat it. This thermal initiator will break apart and form radicals. That radical will form polymers. And so the way we do this is we put these liquids into glass jars, put them into ovens, and we have to very carefully heat these because this is a very exothermic process. So if we just heat these up very quickly, these will generate too much heat and explode. And so this whole process needs to be done very carefully. And so this is why everything is done very slowly to make these reactions go slowly so that they don't generate too much energy at once. So in our lab, this takes about 5 days. When I talk to industry, so Elgin is the main company in Sweetwater, Texas, of the plastic scintillator, commercially available plastic scintillators in the United States. And they tell me that it takes 9 to 10 days when they're making these in bulk. So, okay, just remember that 5 to 10 days, it's a long time to make these materials. So they need to be high quality plastics. This is a time and energy intensive process. So you can imagine, when the company is making these, they're making, hundreds of kilograms of these things in large vats, in large ovens, and heating for long periods of time. So this is very energy and time intensive. Also, I didn't mention, but all of these glass jars need to be oxygen free. So all the polymerization needs to be done in an oxygen free environment. So you have to basically do some process to put nitrogen ambient in these glass jars. And then also because of it's almost like a water-like material initially, you're limited form factors. And so usually you just make a big slab and then you machine the size that you want. So there's a lot of wasted material here. So the big question is, can we make these pulse shape discrimination based scintillators that have good mechanical properties? And the way that we do that is, as chemists, we make um, we want to make reactive dopants. So the question is, can we synthesize these reactive dopants that can be incorporated and overdoped in the PVT to make them um, have good mechanical properties? So the way, and so hopefully some of you have had some organic chemistry. I won't show too much, but I need to show a little bit just because I think it's important for this presentation. So this PPO was the original dopant that everybody uses, and so we thought, why not use that as a base and make it reactive, and so we made PPO that has this hydroxyl group. That hydroxyl group can be reacted to put what's called a methacrylate. That methacrylate can then be co-reacted into the matrix. And so here's polystyrene, here is this methacrylate functionalized dopant. This can be added in, heated, and then be chemically incorporated into the polymer. And so before, what I showed you was that the dopant is just physically blended in. So it's not chemically attached to the matrix. So these molecules then are free to move around in the matrix. And that's why it, I showed you that picture where it went from clear to opaque. It's because these PPO molecules, when they're simply blended into the matrix, they will diffuse, find each other, aggregate, and crystallize out. So our goal was to see if we could anchor these dopants into the polymer matrix so then they are chemically bound and then no longer can diffuse. So the first time we did this, here's PPO, just the regular molecule. This works up to 30 weight percent. However, this will eventually become opaque over time. But when initially made, they look great. Our problem was that when we added this little group onto the PPO, it made it insoluble in the matrix, and so we could not make a transparent scintillator. So then we had to go back to the drawing board, and as chemists, we knew how to tackle this problem. And so the good thing was that we could just simply make this one precursor and then use that to generate these alternative dopants. And so in this case, we're adding another group on here that is 2 carbons and then the hydroxy group. Here is 1, 2, 3 carbons and the hydroxy group. And so now we're putting this reactive methacrylate out here and out here. And what this does is this group is very flexible, and that will hopefully make these more soluble in the matrix. And so that's exactly what happens. So when we put the 2 carbon spacer and 3 carbon spacer, now we can have these scintillators with large amounts of these fluorescent dopants that are now chemically bound, or we hope they're chemically bound into the matrix. So then we sent these off to our collaborators who test these in front of radiation sources. And they actually did quite well. Not as good as when it simply blended in the PPO, but you can see that we got values of 1.44, 1.64, and these are very, very good numbers. Usually, in order for it to be a viable PSD capable scintillator, it needs to be above 1.3. And so we're doing just great. So that was the first criteria that it passed, was that it worked really well. The next thing, so here is looking at the figure of merit as a function of how much of the dopant is inside. And so with this 3 carbon dopant, you can see that we get pretty good figure of merit. And the next hurdle that we wanted to pass was that it maintains the hardness over the different amounts of the primary of these reactive dopants. And so here, as you can see, the hardness when you just use the physically blended dopant is very low. However, when we use our reactive dopants, it maintains the hardness across all dopant concentrations and maintains high glass transition temperatures. So that's great. So now we have good pulse shape discrimination. We have good mechanical properties and thermal properties. So the last thing we wanted to check was to make sure that these dopants are chemically bound into the matrix so that they don't diffuse out. And the way we do that is we put our samples in one of these thimbles. This is called a Soxhlet extractor. This is a hot ethanol. It will continuously boil up, condense. And so this cycle is done about 20 times. And so it's just, whatever is leachable from the dopant will end up down here. And then we remove all of the solvent and test what is coming out of the scintillator. And so we do this by NMR, so nuclear magnetic resonance. And so these are with our 25 weight percent reactive dopants, nothing is coming out. This is basically telling us that nothing is coming out, but when we use just the blended PPO, almost all of it comes out. And so that is kind of an indirect way of showing that our reactive dopant is chemically bound and not leaching out. So this demonstrates that this project worked really well, and we're still working on this. We're trying to use different dopants because the methacrylate-based dopants have some issues, and so now we're making reactive dopants that have styrene functionality and are working on this. And so this is basically the first project I wanted to talk about, and I have about 20 minutes left, it looks like. So I will move on to the next project, which we worked on, was to see if we can make that long fabrication time of 5 days shorter. And so the first way we did this is by trying to do a photopolymerization process rather than a thermal polymerization. So can we make good scintillators in less time? And so let's see if this worked. So maybe some of you are aware or have had some cavities in your teeth. And most of the processes used nowadays are light photo-induced polymerization of these materials into your cavity. So it's basically a methacrylate or styrene functionalized material that is now used in conjunction with a photo initiator rather than a thermal initiator. And so this is what is used in dental composites. It's some kind of a methacrylate monomer, um, some silica filler, and that is then the light is put into your mouth, focused on that cavity where the material has been deposited, and it is photopolymerized. And so we wanted to take advantage of this known process to see if we could make it work for making scintillators. So the light comes in, it makes radicals in the same way it does the polymerization. So it differs because now you're using photons rather than heat to initiate and propagate the polymerization. So we just replaced all of the materials that would otherwise be used in dental composites with our materials. So some kind of a dopant, some kind of a, vinyl toluene, and the photoinitiators. So first thing was that we were able to do this. It took quite a while. This is a lot of formulation that we did. We used just a regular, LED that we got from Amazon, and we shine light for 2 hours, and then we put it in the oven for another 24 hours. And this is the chamber. Basically, the first chamber that we did this was just a mirror chamber with two LEDs shining light. Very simple process. So bottom line was that we were able to make a sample that was mechanically stable, mechanically hard in 1 day versus the 5+ days using the traditional thermal process. So I'm kind of fast forwarding quite a bit. This took us a couple years to get this to work, but we got it to work such that we're now reduced the time from 5 days to 1 day. So how do these scintillators work? So here are graphs that show in blue is the photo polymerized samples, and yellow is the same, basically the same amount of PPO dopant for thermal polymerized. So this is the figure of merit. So a little bit less than the thermal initiated, but still very, very good. The light yield is also very good, and then the hardness is also just as good. So, um, so yeah, this is all, so this is all thermally initiated with some kind of a cross linker. So I didn't get a chance to talk about that, but we also tackled the issue of having reduced thermal properties, mechanical properties with the increasing amount of dopant by using these cross-linkers. So all this is showing is comparing our thermal process to our photo process and showing that it works. And we can make it in one day. And so this is all very good news. So again, this project again worked really well. And so I didn't mention before, but these references at the bottom of the slides are the papers that we published based on these projects that I'm describing. So now we have um, we've made these reactive dopants that can tackle the stability and mechanical property issue. We've used the photopolymerization process to tackle the time issue. Um, so this is a viable option, and we're currently trying to work with Elgin to see if they are interested in using this in their process, because if they can reduce the time from 5 days to one day, that will save them lots of money, just because you're not using those ovens for that period of time. So anyways, so future work, again, we're trying to get away from these methacrylate monomers. We're trying to um, use different polymer matrices. We're also trying to use reactive dopants into these photopolymerization formulations, because in the first round we weren't using reactive dopants. And so those scintillators that we made are susceptible to the stability issues that I described earlier, that the dopants can still diffuse and create an unstable scintillator. So these are currently projects that we're working on, incorporating photoactive dopants into the photopolymerization process. And this is also the strategy that we used for using the 3D printing of the scintillators that I won't have time to talk about, but we were able to make formulations that we could use in standard 3D printers and make samples in a period of seconds. And so we're able to again use this process to use in 3D printing. Let's see, the next project I wanted to talk about was to change the matrix. So everything that I've been talking about so far has been polystyrene-based matrix. So we wanted to see if this could work in polysiloxane or silicone-based matrices. So these, of course, silicones are flexible and elastomers, and so that was one of the reasons is, can we make flexible um, elastomeric-based scintillators, and can we do this in even less time than one day? So one of the things that we had to learn early on was that the polysiloxanes need to have a high aromatic content, because the energy of the incoming ionizing radiation needs to be transferred to the dopant. That's just a fundamental way that these scintillators work. And so many of these polysiloxanes do not have aromatic content. And so we had to find some. And so we searched and we found some commercial available polysiloxanes. And there has been papers published in this area. There's a group in Italy, the Quarenta group published these polysiloxanes. So here's just showing the chemical structure. These are alternating oxygen, silicon, and the silicon you can see has two aromatic groups. Some of the monomers have two methyl groups, and so you just need to control this. And so they were able to buy these, incorporate some kind of a dopant, use some kind of a process to go from a liquid polysiloxane to a solid polysiloxane. And this process is using this hydrosilylation. So this is just a simple heating process where these vinyl groups within the polysiloxane chain will interact with these silicon hydrogens and form these cross links that converts these liquids into solids. So, the one thing that's really nice about these systems is that they're, again, not air sensitive. They end up being flexible and elastomeric. And we don't know if they can be made into pulse shape discrimination capable scintillators. So this is the one area that when we started working in this, we had no idea if this was going to work or not. So first thing we did again, like I mentioned, was we had to find these polysiloxanes that had high aromatic content. And one indirect way of looking for that is looking for polysiloxanes that have high refractive indices. And so usually if you have a refractive index of greater than 1.5, that is an indication that your silicone has aromatic groups. Because most of the time, the company won't tell you what's inside their silicones. And so indirectly, you have to use the refractive index to give you an idea of how much aromatic content there is. So we tested a bunch of these systems and we, narrowed it down to a couple from a few different companies. And so here you can see we just started off taking again, this original dopant, and then we moved on to a secondary dopant that we actually make in our lab that seems to work better than the commercially available systems. And so we were able to incorporate this PPO into these siloxanes, one up to 5%. Over 5%, it didn't work quite well. And so remember that in the polyvinyl toluene-based systems, we needed about 25 weight percent in order for these to achieve good pulse shape discrimination. So we were kind of worried because we were stuck at 5%. The good thing is that you can just simply mix these dopants into these silicones, heat them for 3 hours in an environment that's not sensitive to oxygen, and go from a liquid to a final scintillator that you can handle with your hand in 3 hours. So we've gone from 5+ days to 1 day, and now we can make a scintillator in 3 hours. But does it work? So we were surprised and still trying to figure out why this works so well, but we were able to show that these scintillators can achieve very high figures of merit at very low concentrations of these dopants. So these are achieving the type of figures of merit that polyvinyl toluene-based systems need 5 times more dopant. So this is about where PVT is, and that needs 25 weight percent of this PPO, whereas in these silicone elastomers, they only need 5%. And so this EJ299 is a Elgin control product. So this is like something that we buy and use as a control to compare our system to. So you can see that these 5 weight percent systems are performing better than the commercially available PVT-based scintillators. And the light output, this is the light yield compared to the commercial sample. So roughly 90-ish percent. So we also, in our lab, develop our own dopant. And so this is a dopant that we use quite often, and other people are using it now because it performs better than PPO in some cases. So now we made the same samples comparing our dopant with the PPO dopant. And we find that our pulse shape discrimination is as good and the light yield is even better. And so in this case, our dopant works better than PPO. In polyvinyl toluene, there maybe it works a little bit worse. And so these are all things that we're trying to look like at fundamentally why these things happen. So So yeah, so basically now we can make a PSD capable scintillator in 3 hours. This is after many months. You can see the PPO is less soluble in these matrix, so it goes opaque, whereas our in-house synthesized dopant still looks good. And so we're still publishing papers in this area, looking at stabilities, looking at different matrices, different dopants. But yeah, so you know we've gone again from 5 days plus to 1 day to now to a few hours to be able to make scintillators. All right, so the last topic that I will quickly go over is what's referred to as organic glass scintillators. So they're related very closely to the PVT-based scintillators, except in this case, the matrix and the dopant are basically the same thing. So this was a paper published by Joe Carlson and Patrick Fang at Sandia National Labs at Livermore in 2016. They basically made this molecule and they simply melted it. And as organic chemists, you can design materials such that they do not crystallize. So this will melt and it will form a transparent product that will remain relatively stable and not crystallize over time. So this is what they reported. You melt these, you pour these into a mold, you can machine them and process them relatively low cost, and the light output is much better than one of the best materials known, which is a still beam crystal. Still beam crystals take many, many days to make, and you're restricted to the size that you can make these, but their performance is amazing. But now these organic glasses work even as good or even better. So now the way that they're plotting these is different than I showed before. Instead of using it on the vertical axis, they're using it here. And it's basically, they're showing you now PSD's values of 2.3. Remember, I was showing you ours were about 1.5, 1.6. So these are much better, and they're much better at just discriminating, between the neutrons and the gammas. And so here is the OGS compared to transtillbene. So at the time of this paper, not as good, but now I think they are much better. So the problem with this as a chemist is that one of the processes uses what's called butyllithium. Butyllithium is an extremely reactive material that will spontaneously flame in open air. So we don't like to use this in our group, especially because in order to make a sample like this, you need to make like 5 or 6 grams. And so that means you need to scale up these reactions, and scale up reactions with a very reactive material is something that I don't like to do. So we wanted to work in this area and try to develop a better process. So again, this is how they're made. You heat them up, you pour them into a mold, you generate this beautiful crystal, you polish it. And the way this is, this is designed by having the central scaffold, which is the silicon, and here's all the um, fluorescent material. So there's the central scaffold at which these are forming a tetrahedral. So this is not flat. You have to look at this as this group is sticking out of the screen. This one's going into the screen. So these are, this is like basically a spherical molecule, and that's what gives it its amorphous properties. So it must have high aromatic content, which it does because it has this high concentrations of fluorescence groups on it. So it has the bulky aromatic fluorophore. It needs secondary dopant. So in the melt, you're adding a secondary dopant as well. And these must be very pure in order for them to work. So one of the problems with these systems is that they are very brittle. So once you make them and try to machine them, they can chip and they can crack, and it's tough to work with them. So our group very recently, so this is data like a week old, we've been able to make organic glasses using a very simple chemical process that's really mild and is high yield chemistry, but now are making these organic glasses that are very tough. So you can drop them on the countertop. They don't chip, they don't crack. They can be machined very easily, and they have a very good PSDs of 1.8. This is tested at Sandia, so we're collaborating with Sandia on this. So now, yeah, these are the type of scintillators that we're able to make now. So good light output, good PSD, and so we're just at the very beginning of this. So we're very hopeful that this will lead to even more promising results in the near future. So it is 11:45, so I'll wrap up. So I just have a conclusion slide that we have been successful in producing PSD capable scintillators that are stable. We've reduced the time to make these from 5+ days to 5 hours. We've used alternative matrices based on polysiloxanes that are promising alternatives to polystyrenes and can be made very quickly. And we are able to design and prepare these new OGS materials for mild processes to give us very promising new scintillators. And the other thing that is we've been successful in order for this projects to work, we need to have very good collaborations. So I think we are able to make quick progress because we as organic polymer synthetic chemists are very we are collaborating with nuclear scientists, and this is what makes this project successful. So this is an acknowledgement slide. So all of these young chemists are doing all the work here. We are part of the ETI consortium out of Georgia Tech, and we work closely with Patrick Fang and Anna Erickson on these projects who do all of the radiation detection. And Tristan and Dina are actually in Livermore for the summer working with these groups. So with that, I'll wrap up and take any questions that you have.
All right, thank you, Dr. Solinger, for that presentation. There's a number of questions in chat already, and I will start going through those. If you have any more, please add them to the Q&A section. So there was one question about safety in lab testing, and the question was, how is safety of the lab/testing unit ensured when heating takes place for a long time?
Let's see, can you repeat the question? It's about how heating.
Yes, how safety testing is ensured whenever you're doing the heating process for your scintillators.
Yeah, so that's a big issue. So, not only are these, so I'm assuming they're talking about the vinyl toluene to polyvinyl toluene conversion. So yeah, this is a very tricky process. It needs to be done very slowly. And, we've had vials explode in the oven if the oven is not ramped up carefully. And so this is one of the reasons why we're interested in going away from PBT is because it's a dangerous process, and the companies that work on this, they need to they need to be concerned about this because they're working on hundreds or thousands of kilograms doing this conversion, and so it's a really big safety process, not only because of the potential for these exothermic reactions, but also because these are volatile materials. So if you're heating up these materials, they can evaporate and they can, become, airborne and be breathed in. Yeah, so there's a lot of things that need to be concerned. And one of the reasons why we are shifting our focus to silicones and organic glass now. Great question.
There's another question about wavelengths. So is there a specific wavelength of light that's used for photopolymerization?
Yeah, that's another great question because you can imagine that when we're using photons to do the polymerization, um, our dopants are absorbing a lot of those photons that should otherwise be used for doing the chemical reaction. So we had to work on choosing the right photo initiators, choosing the right wavelength of light in order to make this work. So most of the most of the 3D printers, for example, use a 505, 405 nanometer light in order to do these 3D printing. However, in our system, our fluorescent dopants absorb that light and so we can't do the polymerization. So that's why we had to shift to 365 light for our 3D printing project in order for these to work. So yeah, there's a lot of design that goes into the photopolymerization process and choosing wavelength, choosing photo initiators, choosing the fluorescent dopants as well.
Thank you. There was another question about figure of merit variation. The question was, what's the reason for figure of merit variation between the different polymerization methods?
Um, yeah, that's a good question because the figure of merit depends on basically the difference in prompt and delayed fluorescence, and the delayed fluorescence is related to the generation of triplets, and those triplets diffusing and finding each other and annihilating to generate that delayed fluorescence. So, so the morphology of the scintillator plays a role in this because the triplets need to be able to diffuse to find each other in order to generate that delayed fluorescence. So in some of the systems, the morphology may not be just right, so that, maybe when these triplets are generated, they're too far away from each other and they just don't have enough time to find each other, and then they will just decay through other non-radiative processes. So yeah, there's a lot of work in trying to figure out what type of a morphology is best for creating the most efficient, figure of merit process. But yeah, that's a great question.
There's another question asking about what variation do you see in detector efficiency when looking at batches of plastic scintillators?
And so like looking at
Scintillator, same formulation, I believe.
you mean like the from one formulation to another, or reproducibility?
I think they're asking about the same formulation,
Oh,
but
like
remaking the same scintillator,
oh,
like how
like
consistent it is.
reproducibility.
Yes.
Yeah, reproducibility is always an issue. So, especially when we're making new dopants, um, they need to be very, very pure because if you think back to one of my earlier slides when I showed that you only need zero point 0.1 weight percent of the secondary dopant to funnel all the energy out, that means that, 0.1% of an impurity, can kill everything. So in this case, it's 0.1% of something, that you want, but it could easily be 0.1% of something that you don't want that could kill your whole process. So purity is really, really a big deal. And so that this is actually what's taking us longer in our organic glass project, is just making these materials pure enough. So, the material that I showed with that had the 1.8 pulse shape discriminant, 1.8 FOM value, that one, like after the second purification was only like 1.3, and then after the third purification 1.5, and then, and then 1.8. So we don't know if we're now working on our purification process to make sure that we can, efficiently purify these, in order to make them work really well.
There was another question about if any of these materials break during the casting process, can you reuse any of the components of the broken scintillator, or does that have to be scrapped?
No, that's also the beauty of the organic glasses is that they can be remelted and reused. With the PVT and with the silicones, all of those, if they crack during production, then they're basically gone. You can't reprocess them. So that's another big advantage of OGS is that you can reuse them if they crack.
Thank you. There was another question about general shape. You mentioned earlier in the presentation that there's this shift, a push towards more so CPMs over photoemulsifier tubes. And they asked about, do you think, does that make it so that square detectors are a lot more preferred for these applications? And if not, in addition to that, how do we factor in light reduction using, well, reduction in signal from light guides when but using light readouts such as IPMs?
Yeah, that's kind of not my area of expertise, but I know that photomultiplier tubes are very large. And so I know one of the applications is putting these scintillators on drones. And so if you want to be able to detect an area that you suspect of having some kind of a radioactive contamination, you would love to be able to send a drone into that area. And so, this silicon photodiodes are much more lightweight, so you could easily think about making a drone with integrated scintillator plus silicon photodiodes to do this, because yes. So yeah, so that's, we're not working on that, but we're waiting for this silicon photodiodes to be um, good enough so that we can actually get away from, we as chemists would love to make non-blue scintillators. We can easily make green emitting scintillators. Actually, that would be much easier to make than blue emitting scintillators. So in that case, that would be great to be able to get away from the photomultiplier tubes.
There was another question about efficiency, I believe. They asked about which between organic glass and plastic scintillators, which one's more efficient. I think they might be getting at detection efficiency.
Yeah, I think organic glasses are more efficient at this moment. Um, so yeah, it's unclear whether or not organic glasses can be made in the volume that you would need for these portal monitors because there's a lot of material that goes into that. It's basically like, think about 8 feet by 2 feet. So, 2 meters by, 0.8 meters of plastic. But maybe with the organic glass, you don't need as much because it is more efficient. So it's unclear what is the primary application for organic glasses. Would they be more efficient in using in um, handheld devices or in drones, or can they be used in portal monitors? I don't know that that's possible. But yeah, they seem to be much more efficient in terms of light output and pulse shape discrimination. And I didn't get into um, the thermal neutron detection. So we have another project making boron 10 that we can use to detect thermal neutrons. And so we can make um, triple PSD capable OGS as well.
Well, thank you. I think that we're just at time moment. So thank you to Professor Selinger for giving this talk today, and thank you to all of our participants who showed up to all these different lectures.
Yes, thank you. My pleasure.